Well, right, last time we were focused on, I have a situation here. I tried to find area to curve, and our general strategy was, we broke this up into a whole bunch of different subintervals. And we made little boxes. Built this up with boxes, like this. Built this up with boxes and got an approximation, and then we took a limit computation of what this is. Now, the big assumption that we had was that this was actually an area that is this function is above the x-axis. So that it makes sense to talk about this as an area. There's no reason strict to positive functions. So, in other words, we can perhaps deal with something that goes like this. All right. And there would really only be sort of one difference in the first two. What we would do, I think, is break this up. The little subintervals again. And maybe we would use points. We use these test points inside here to determine height. But notice that the place where the function is positive, I get a positive height in the box. But over here, for example, so notice the width of each of my boxes is still the same. The only difference is if this thing is hanging below the x-axis, it's going to get sort of a negative value. So these, if you will, sort of play this back to release these boxes over here will give you a positive area. So positive height. These boxes here are hanging down, so and then will give you sort of a negative height, and so therefore a negative area. So we now approach this for a general. The longer, but yeah. What we do is sine or net here. So let's think about this problem. Let me kind of example here. Let's kind of warm up here. Suppose here's some -3. So if I were to graph this function, and what we call this, public generalization. Uh, Definitely. So it's basically this process, finding boxes, this time they can paint down, and have sort of a negative height and therefore a negative area. And taking the limit, because of that. So what would happen in this case here? Okay, so what does this function look like? Interval minus one to four. Well, it looks like a horizontal. Now, if I break this up into boxes, hope you'll see that if I break this up into boxes here, then it doesn't matter where I pick the point, the height is always the same, right? Because this function is constant. No matter where you plug it in, you go with the same value being three. Make those boxes smaller and smaller, and really basically what you get is the same down here, which the answer is. Uh, Not 20. So how wide is it? There you go. This should be negative 15. Right, because the area of that box is 15 is hanging below the x-axis. These heights of the boxes are all negative. What about this? Uh, so, let me draw a picture. Maybe that'll help. So it's like 4A. And it's point of negative 2 minus 4. That's good. Let's get that. I, area. Right. I mean, so what do? We make little boxes here, right? The ones over here are hanging down. And they're gonna give you a negative area, and at the end of the day, it should give you the area that's triangle here, but negative. The axis, right? Over here, boxes are all above, and it should give you the positive area. Area of this triangle is, let's see, it's got height 8 and facing 4, so this is area 16. And the area of this triangle actually is 4, but it's minus because it's hanging below the axis. The height of the box is going to be negative. So it should be. By the way, this notation that well, take this. Take the row, it's like sign, and then but that's 5 minus. Okay, you're at a skewed picture. Oh. That's essentially that. Put together this bit, and this bit. If I draw this bit, it should be the size of this. This is love. So you should get. Okay, so let me give you kind of a formal bit about what the depth interval is. And then we'll go back to the same question. Okay, so here's the general set. First notation. The definite alphabetics on the interval from A to B noted. So this part These are called the limits of integration. And they're basically the endpoints of these intervals, right? This is just the interval you're looking for this on. And f of x is called the integrand. It is the function that you're trying to find this number for. Okay, so here's our general setup. Take AB and partition into subintervals with endpoints and choose xk star in subinterval xk minus 1 xk. So this can draw a picture of this going along here. So what we do is we take the interval from A to B, and we call this x0. We call this xn. Just we keep with our other notation, and we choose the subintervals in here, not necessarily in this case. This is just like we did last time. And we choose a test point in each subinterval. And this is, just as before, this is the one that determines height. The only difference now is the function might be below the axis. And your height, use the term loosely, might be negative. So you put some random point in here, some star, x star, x star, x star, any point in there, and in general maybe star. And just choose points here to determine, instead of saying height, I'll say value function. So you plug those in the function to get the value. Just as before, now form the Riemann sum and this is an approximation of our definite interval. This is where we're going with this. This is an approximation of it. And this is again, this is the same thing that we were doing before. This is a height times a width. And the caveat here, of course, the height and value function can be negative. Now we define the definite interval to be the limit of this. So the setup is the same as we're doing before. We just break this up into pieces, compute all the little, figure out all the little widths. That'll be done. Got this here to note as before. Delta xk is xk minus 1. So this is just the length Okay, there. This is delta. So how thick the maintenance was. Now, we define. Definite interval. Here's our new notation. One side. Yeah, I need some kind of limit, right? So what am I doing? I'm taking this sum and I'm making the boxes more and more of them. So this is kind of a so question. This was a little bit, you gotta think about this a little bit more than with the derivative. The limit as what? Okay, what's it? Oh, right, as n goes to infinity. That's a great idea, but it doesn't quite work. Right, there's actually, there's, this is kind of subtle, it's a subtle problem. Seems like. No, what the problem is? Here's how, so your idea is exactly the right thing to start on, right? Let's think about what happens if you set into it. Suppose I have this function here. Let me show you how. it is. Suppose I did this. Now suppose what I do is this. Suppose I use my right hand endpoint as. So 50 little boxes. Now, so you can write. Now, let's suppose that I'll let the number of boxes go to infinity, but I'll leave this gap here, right? So I'm making more and more boxes, but I'll put them all to the left or to the right of this box, right? I'm letting n go to infinity that way. What's gonna be the problem with that? So this box always stays static, never moves, but I'm adding more and more boxes in here, more and more boxes in here. At the end of it, what's it gonna look like? When you take the limit, isn't it going to look exactly like this? You'll get exactly the area under this. You'll get exactly the area under this. And then you've got this one box left over. Quite opposite. See how I cheated there? I put, instead of making everything exactly right, this box stays fat. And I get more and more inflating boxes here, so to speak. You see what the problem is with letting n go to infinity? Because I could do let n go to infinity that way, right, and screw things up. How can we get around this problem? Any ideas? When I let these boxes over here, when I let n go to infinity and keep this in fact, what happens to all these boxes on the left and right? What's happening to them as they get more and more boxes? What's happening to the widths of them? The widths are all getting smaller, right? But this one's still staying big. Isn't that the problem? Right? This one stays wide. The other ones get very skinny, right? And what we want is skinny boxes. We want uniform skinny boxes. We don't want a couple of fat ones and everybody else to get skinny. We need everybody to get skinny to get the right area, right? So, how about this? This limit means the maximum thickness is going to zero. What this is doing is this forces all the boxes to be skinny. Because what this is saying is even your fattest box is getting skinny. It's going to zero, right? Notice that if that happens, how many boxes should you have in the limit? Yeah, you're going to infinitely many boxes, right? When you make them skinny, there has to be infinitely many. But if you make infinitely many, they don't have to be skinny. That's what the problem is. Everybody see that? By the way, let me ask you this. So, let me make a mark here. Want all boxes to be thin. Uh, okay. Notice that this does mean that there has to be, there's no bound on the number of boxes. The number of boxes going to infinity, it's just goes to zero. But just because you make the number of boxes go to infinity doesn't mean this has to happen. Everybody agree with it? Let me ask you this. Um, this is the definition. Okay, so, by the way, let me say a few things and I'm gonna say something else. Max Hill, please. You are going to learn in this class and also in, 10A, some fancy ways to evaluate this, right? The only way that we know how to do this really so far is number one, recognize it's an area, or number two, do this limit, right? Now, there's got to be an easier way to do this, otherwise people wouldn't have to do this. And we're going to see that there's an easier way to do this. You are going to learn some fancy tricks in this course, how to figure out what this is. And actually, this comes up all over the place, right? Basically, this is a way to approximate sums. Sometimes it's easier to do an interval than it is to add things up. So it's a way to approximate sums. This gives things like position, you get velocity. This can give things like population, all kinds of models in economics, models in all kinds of science and engineering. This is incredible. It's good. And like I said, it's good for, I've even used this to approximate something. So it's incredibly useful. No matter how many tricks you learn, however, it is important for you to remember that at the end of the day, this thing is a limit of a bunch of a sum. It is always a limit of the sum of this thing. If you remember that this thing is a limit of a sum, it will make doing integrals a lot easier for you. You won't have to memorize a bunch of formulas because everything that a lot of the stuff you do in 1080 comes out of this limited sums thing. If you remember it that way, it'll make it easier. Here's another thing. There will be some problems where this is intractable to do. However, this is equal to this. So if you can't figure out what this is exactly, since it comes from this, all you have to do is make enough boxes and you can approximate this. So that's another good reason to remember that this is a limit of sums. Okay. So any questions? All right. So we say that this thing here limit technically not this takes k goes to 0 of the sum now, of course, the first thing that you might ask is, well, what if this limit doesn't exist? And this is why we have to do it generally, because this limit for this thing to work out, this limit should exist no matter what choices partitions I make, no matter how I break up this interval and how I do the test points, we should get the same answer in the limit. So for example, Richard, if we both break this function, or break this interval up the same way, and I choose the left-hand endpoint, and then I take a limit, and you choose the right-hand endpoint, and you take a limit, and you and I get different numbers, this theory is no good. It's crappy, because it shouldn't make a difference how you do the process, how I do the process. When you take the limit, we should get the same numbers. Otherwise, we need to chuck this in the garbage, right? Because if you can do the process and get 2/3, and I can do the process and get 17, that's a problem. It's not telling us anything good. So the natural question to ask is, when does this limit exist? Here's the good news. And it's rather ironic because it's much easier for this limit to exist for a function than for it to have a derivative. This is actually an easier limit to exist. However, it's harder to compute for a lot of functions than the derivative is. Right? So even though this limit exists, the interval exists, sometimes it's difficult to actually compute in both form. You have to approximate. So if this limit exists, that is to say, if this interval exists, then we say the function f of x is integral on the interval domain. So when I say a function is integrable, that just means it's integral since you can integrate it. That limit exists. You can get a number. So here's a theorem. If f of x is continuous, on a thing, or in fact, it's much looser, is bounded and has only finitely many discontinuities, on AB, then f of x is integral. So any function that is continuous, if you can draw the function on AB without giving up your principle, you can integrate. Period. Not only that, if bounded, right? So think of it this way, it doesn't have any vertical asymptotes or horizontal, it does, I'm sorry, it doesn't have any vertical asymptotes on that interval, right? And, it's only got finitely many discontinuities, then it's integral. So for example, function looks like this. That function is integral. It's not differentiable, but it's integral. It's not even continuous, right? It's not continuous at A, it's not continuous at this point, but it's integral. So it's much easier for a function to be integral than it is the differentiable or even continuous. So that's kind of a let me ask you a question. In the problems that we did yesterday, so let's do an example. Uh, let's do these two. Gosh, how obnoxious. I give you two problems, same function. Any suggestions on how to do that? Or any predictions on what any of these should be? I predict this one. So here's my prediction going in. That one should be. Anybody? Well, right, but again, you're beyond kind of where we're at here. What kind of function is that? It's cubic, but is it an ordinary function or is it a little bit odd? This is not a function, right? Because f minus x is minus x. So this is a symmetric interval about origin. So here's what I'm thinking. Thanks. Yes. I'm thinking that these areas should cancel out. Let's see. So let's do this problem. I don't want to go through two limits. So let's just put in dummies for the endpoints A and B and figure this out. And then I should be able to plug things in. So let's set this up. We're going to do our computation. So we're going to take the interval from A to B. And we're going to split this up into n evenly spaced. So So the thickness of each of these, what should it be? Right. The length of that interval is B minus A, and the number of pieces is N. Everybody okay with it? Okay, we'll also use right endpoint. Term. Uh, function value. I won't say height. Okay, so I guess I need to figure out what the right endpoint is. Right, and then I've got to plug it into that function. Yeah, but. So. So we break this up into n subintervals. So I'm going to use the right endpoint. There's x1 star. There's x1 star. It's not A. I'm using the right endpoint, the left one. So how much do I change it from that? Kick it over. 1 bit. What do you suppose x2 star is? You need 2 bits, right? X3 star, you need 3 bits. And hey, here's a good check on this. The last one of these should be X installed, right? Do I agree with that? What should X, according to this formula, what should X install be? So, we have A plus N times B minus A over N. A plus. So it should be B. And that's exactly what it should be. It should be the right end point of the last one should be B. So I'm pretty sure this formula is working well. Okay, so let's form the Riemann sum. Sum f x k star delta x k, which for our case, this should be f of whatever this awful thing is, a plus k is b minus a times delta x k, which in our case is b minus a. Okay. And the last thing I got here, I guess, is my function. Like, and actually, what I'm going to do here is I'm going to pull this b minus a over and out the front. I can do that, then that decays there. So this is b minus a over n. Sum. Let's see, what is my function? 4x cubed. So that should be 4 times a plus k b minus a over n cubed. Let me remind you here. Because so I'm going to use this formula here with the role of x being played by a and the role of y being played by that mess. So this is b minus a over n times the sum 4. Okay, what do I gotta do? Well, I'm gonna cube this. That squared times 3 times this. Three a times that squared. And finally, that cube. Uh, oh, my bad here. I've got my take cube there as well. Okay, this is mass. I'm gonna write this as 4 sums to make my life easier, believe it or not. This is step of purposes. This is 4 a cubed plus 12 a squared k b minus a plus 12 a k squared b minus a over quantity squared plus 4 k cubed b minus a over n. So I'm gonna write this out as 4 sums. This is going to be 4 a cubed b minus a over n times the sum a 1 minus a. Sum of this. Now let's see, for this one, I'm gonna pull out 12a squared b minus a over n. This plus 12a squared b minus a over n squared. Sum a1 k. Okay, so I'm focused on here. This one I'm gonna pull out 12a b minus a squared. So that's going to be 12a B minus A over M cubed. Squared. And finally, I'm gonna plug four over B minus A over Q. Four B minus A over M. Fourth power sum A Q. Okay, let me let you all catch your breath here. I want you all to make sure that you follow me. Everybody okay on this? Fine. The first one, I pull out four A cube, leading me to just summing one. And there's always that B minus A over in there. And I pull out 12A squared, B minus A again. So I'm not going to pull out squared, B minus A over squared, sum of K. Then I pull out 12A, B minus A over N squared, 12A, B minus A over N cubed. That's a sum of K squared. Finally, pull out 4, B minus A over N cubed. And I get this. Okay. Any questions? Okay, what might be my next step here? Right, so I've got a little formula for some of these. Okay, you might remember what this one is. What happens when I add up one to itself? One plus one plus one, n times is going to be n. I remember what this one is. One plus two plus three plus four all the way up to n. That's up to. This one, n plus one, qn plus one, 6. This becomes n squared plus 1 squared. I gave you all those formulas last time. Just find those. Okay, so let me simplify this a little bit more. This n cancels the n down here, and this is 4 A cubed B minus A. This is 12A squared B minus A squared times n plus 1 all over 2n squared. But 12A squared B minus A squared over the top. I have n plus 1 on the top, and I have 2n squared on the bottom. Plus this bit on the top, I've got 12A B minus A cubed n plus 1, 2n plus 1. And in the bottom, what do I have? I have 6n cubed. Finally, this last bit here, having 4 B minus A to the 4 n squared n plus 1 squared over 4n. This is what my Riemann sum gives me, this approximation that we're using in boxes, right? N equals one, put in that, and that'll give you what it is. N equals 100,000, put in N equals 1,000. Okay, so let's practice kind of going fast here. What happens here as n goes to infinity? So but wait a minute. Didn't Richard just answer this for us a while back? And didn't I sit there and say, well, no, you gotta make sure that the max thickness goes to 0. How can I just let n go to infinity here? Right? And my contradiction about told Richard that, oh, look, even the fattest box has to get thin. Now I'm just being sloppy and letting n go to infinity. What is it about the problem that lets me let n go to infinity? What assumption did I make about my boxes? They're evenly spaced, right? Which is not an assumption we made in general. But if the boxes are evenly spaced, they're always going to be evenly spaced, and I let n go to infinity, they all have to be getting thin, right? Because they all have to be, they're all the same size, right? They all have to be, right? Okay, with that. So let's let n go to infinity. Let's practice. There's 4 terms here. Let's kind of practice what we did. As n goes to infinity, where does this piece go? Where does that first piece go? It just goes to itself. There's no n at all, right? Doesn't depend on n. So this is 4AQ d minus a. So I'm going to roll bracket over here. How about this one? What happens to this thing goes to infinity? Biggest power that I see on top is n squared, right? Biggest power on bottom is n squared. That's its half. What multiplies the n squared term on top? This ugly thing. What multiplies the n squared term on bottom? That. So it's the portion of 6a squared b minus a. What about this one? This thing goes to infinity. What's the biggest power that you see on top? It's a cube. You get it through 2n times n times n. What's the coefficient of the n cubed term? It should be 2 times this, 24a b minus, or b minus a. But you get that extra 2. What's the coefficient of the cubic term on bottom? 6. So I get 4 a b minus a cubed. Biggest power I see on top, 4. Biggest power on bottom, 4. What's the multiplier of the end of the 4 term here? It's 4. B minus a 4. On the bottom, it's 4. So I get everybody okay with that? Any questions on how I got any of that? Okay, so, this is of course the correct answer. But let me see if I can simplify this a little bit. Let me multiply this out. This is four, A cubed B, I think we'll see American minus 4A4. Plus, this bit is B squared minus 2AB plus A squared. So that's going to be plus 6A squared B squared minus 12A cubed B plus 6A4. This bit right here is B cubed minus 3B squared A plus 3B A squared minus A cubed. And so when I multiply that by 4A, I get plus 4AB cubed minus 12A squared B squared. So 4A, yeah. Plus 12A cubed B minus 4A4. And finally, this last bit, most obnoxious involved is B4 minus 6 B3A, not 6, 4, minus 4B cubed A plus 6 B squared A squared minus 4 B A cubed plus A4. Multiply that one out, and so you just get that plus B4 minus 4 B cubed A plus 6 4 A squared B squared minus 4 A cubed B plus A4. And so, so what do I get here? I get, let's look at, there's only one B4, isn't there? Well, I've got that covered. Let's look at, B cubed A terms. There's a B cubed A. There's a B cubed A. And that seems to be it. They cancel out. How about A squared B squared terms? There's a 6A squared B squared minus 12A squared B squared plus 6A squared B squared, and they cancel. How about A cubed B terms? There's one. A cubed B minus 12 A cubed B plus 12 A cubed B minus 4 A cubed B, and they cancel. And what's left is A4 terms. I've got minus 4 plus 6 is 2. Minus 4 is minus 2. Plus 1 minus 1. This is integral from A to B of 4x cubed. How many of you want to do this again? Not me, right? This is really cool because we found this interval. And this gives us an area under the curve. So let's answer the question. My original question is, so the integral from -1 to 1 of 4x³ could be 1³ minus, or I'm sorry, 1⁴ minus 1/4, which is 1 minus 1, which is 0. That's what we do. What about this other one? The integral from -2 to 4, 4x³ dx is 4 to the 4th minus -2 to the 4th. So 4 to the 4th is 256 minus 16, which is 204. So the heavy lifting to get this formula made this problem easy. The problem is the lifting was kind of heavy. Nobody wants to do this in general. And I'll give you another example of how it works and give you a little extra credit for that. I'll give you an extra credit off. So, everybody with me so far? Everybody understand what this is the process we go through? I'm hoping that in this course we will find an easy way to do this, because if we have to go through these limits every time, it's going to be enough. It's just not very fun. So we need to discover something else. And rest assured we will. There is a better way. We'll get to on Monday. But for now, let's look at some properties of intervals. Let me one. So here's some properties. Suppose f of x and g of x are integral. So what's up with this? Then number one, the integral from a to b You know how we set this up all the time, and I said, let's break it up into evenly spaced intervals and let's use the right endpoint. This is a computation. Let's use evenly spaced intervals and right endpoint. Basically, if you just use this formula, you will get exactly what I used in the previous example with 4x³. I derived this from scratch, but here's the general formula for it. This thing right here is the width that I can pull out of the sum, and this is the function using the right-hand endpoint. Plug the right-hand endpoint in the function, take the limit. Now, why is n goes to infinity? Because I'm assuming at first that it's integral. That means that any limit exists, no matter how I break it up, no matter what points I choose, the limit always exists. So if I want to compute it, do the easy limit, so to speak. Right, okay with it? Okay, so I bet you guys have some of these. What should this be? The integral from a to a. You started A and you ended A. This should be zero. There's no thickness to it at all. Right? Your interval from A to B is just the interval from A to A. There's nothing there. What do you suppose the relationship between these two are? What if you integrate something backwards? Instead of going from A to B, you go from B to A. Well, if you go backwards, now your widths going from B to A are all negative, so it should change the sign. This is actually quite useful. If you invert the limits on an integral, if you integrate backwards, so to speak, then it's basically sign change. Number next one. The integral from A to B of f of x plus g of x Why is this true? This is true because what is an integral? See, here's the, kind of my first moral of the story kind of thing. What is an integral? It is a limit of sums. Can you split sums up into two separate sums? Yes. Can you split limits up? Yes, if they both exist. And that's what we're assuming. So since an integral is a limit of sums, you can write the sum separately. You can do the limits separately. They both exist. So that's good together. By the way, this is also true if you replace plus with minus. And that follows from the next statement. What about this? Right, because what's an integral? It's a limit of sums. Can you pull a constant out of a sum? Yes. Can you pull it out of a limit? Yes. So you have to be able to pull it out of a limit. Oh, this was fantastic. This one, we're going to actually use this in fundamental theorem calculus. Integrating from something from A to B is integrating it from A to C and then from C to B. Now, let me give you kind of the obvious version of this theorem. And again, this isn't a proof. I'm just going to hopefully build your intuition a little bit. Intuitively, this is what this says. Let me kind of read this. Intuitively, this means the area under that curve from A to B is the area from A to C plus the area from C to B. You all see that picture? Does that make sense? If this, of course, is C, then what this is saying is this area plus this area is the whole area. But my picture makes several assumptions. Anybody want to shoot holes in my pseudo proof here? Okay, what assumption is in drawing that picture, I assume that this is actually an area, that this thing is above the axis, the x-axis. There's also another assumption. What assumption did I make about C? That's right. I assume C is between A and B. This is even true if C is 50 miles that way. Integrate from A to C plus B or plus C to B, you can still get that. It doesn't matter whether C is between A and B or not. It doesn't happen. So this is true whether F is doesn't have to be a positive function, and C doesn't even have to be in between, still work. So see if you can figure that out. What happens, for example, even in this case, if C is beyond here? And remember, this part might be useful in thinking about that. So remember number 6, because we're going to use that. The absolute value of f of x is integrable. So if f is integrable, so is its absolute value. And the integral of the absolute value of f of x is greater than or equal to the integral of the absolute value is greater than or equal to. And in fact, the integral of the absolute value is, what you can do here is take the signed area, take the area above and the area below, and just add them all up like they're positive. Here's some other kind of common sense ones. I think that you won't be surprised at, but they're useful anyway. If f of x is greater than or equal to 0 on a thing, then the integral from a to b of f of x dx is greater than or equal to 0. So what this is really saying is, hey, look, if I'm drawing my picture and it's above the x-axis on the center ball, then this thing should be greater than or equal to 0, because after all, this turns out to be an area, right? An area of 0. Here's the generalization of this. If f of x is greater than or equal to g of x on AB, then the integral from A to B, what do you suppose is true? What do you think is true about these two? Yeah, that's exactly. Oh, still works. If this is big guy and this is small guy, then the integral of big guy is big. And finally, if this is the way, this is very naive bound, but nonetheless, be useful. Let me draw you a picture for this last one. Um, I'm going to draw this thing continuous. Now, notice that we have from earlier that it says a minimum maximum. Notice that would everybody agree that every red Y coordinate is greater than or equal to M, which is along the blue dotted line? And by the same token, I can think this would be capital M. Everybody agree that every red Y coordinate is less than or equal to capital M, which is the green. What does this say? Well, what this inequality says is, let me point out that this area down here is little m. Right? Because this is just a rectangle, its width is b minus a and height m. And the area of this giant rectangle up here is capital M, b minus a. Because this rectangle also has width b minus a, but it's now it's got height capital. What this inequality says is the area under the red curve, which is in the middle sort of, is bigger than small box, smaller than big box. That's all that says. Everybody okay with it? Okay. Any questions? You'll learn some fancy ways to do these kind of problems later. But this first example, this is actually the sort of always be. That's beyond the scope of what we're doing. Yeah, the answer is yes, but there's a better way to do this. Let's take this piece by piece. Best way for this is to think about this all sort of geometric. Let's do this piece by piece. By the way, let me ask you this. Let me ask you a question. What is that function with, yeah, what is that function? It does, but can you describe geometrically what this is? Right, so if you square both sides of this, you get y squared, minus x squared. Or x squared plus y squared. So this is actually upper half. By upper half because my y is positive. It's only upper half. Circle. Radius. What's the radius of this part of the circle? Because that thing right there should be the radius squared. So really what this is saying, this is what this looks like. This thing right here says integrate me from minus pi to pi. Okay, taking your knowledge all the way, perhaps back to grade school, what is that here? What is that here? That's right. So it's going to be 1/2, well, 1/2, because it's half a circle. Pi times the radius squared. So this is 1/2 pi cubed. Right. And I think it gets a little bit easier. Yeah. How about this? Let's see what this is. Sine function from minus pi to pi. That's what it is. Integrate me from minus pi to pi. Because these two are the same size, and this is negative, this is positive. The sine area is 0. The third one, I think, is sort of similar. Although the last two, you can actually do the old fashioned way with limits, but let's not, let's do areas. So this looks like minus pi, so this is minus pi minus 4 pi, and this is pi 4 pi. Cancellation, right? This area, that goes in the order. This area and this area are the same, right? Plus and minus. And the last piece, integral from minus pi to pi, 2. If I look at this, really what we're asking for is this area here. And this area has height 2 and width 2 pi. So this is 2 pi by 2, so I get 4 pi. So at the end of the day, this turns out to be 1/2 pi cubed plus 0 plus 0 plus 4 pi. So 1/2 pi cubed. So like I said, in this class in 1080, you're going to learn some tricks on how to do these. We're not completely stuck with the limits. because it's geometric stuff. But right now, for most things we have to do limits, but we're gonna learn how to get around that soon. And in fact, we'll get a clue about this on today's quiz. Any questions? Okay, so let's look at the quiz for today.